Hello, we're going to be doing problem number 47 of chapter 34 of Physics for Scientists and Engineers by Knight, 2nd edition. So the problem gives us this interesting square loop here. They say the square loop, I'm going to write this down now, has a resistance of 0.1 ohms for the total length of it. Anyway, so this square loop is rotated 45 degrees, so it's going to be going into a this B field. There's like a boundary here. It's going to be going into this B field at a rate of 10 meters per second. The B field has a strength of 0.8 Tesla. So anyways, what we're supposed to get out of this is that what it requires. Find the induced current of the loop as a function of time. Give your answer as a graph of I versus t from t0 to t 0.02 seconds. And then the second part of the question asks what is the maximum current, what is the position of the loop when the current is maximum. Let's look at actually the thing that we first need to calculate is what is this L here, because it turns out what we really need to know is what the half length of this line I've drawn here is. So just using trigonometry, we can calculate that pretty easily. I left it in centimeters because it comes out nicer. So you have 10 times the square root of 2 centimeters is the length. And then at this point I'll convert it into meters. Square root of 2 over 10, because this divided by 100 here, divided by 100 equals that, and then just so we have it known, the half length, where the midpoint would be here, is square root of 2 over 20 meters. So t equals 0 the second this loop enters the B field boundary here. So we're gonna have to actually divide this up into different phases. I labeled them phase 1, phase 2, and phase 3, and that's because this diamond shape makes an abrupt change in the delta area with respect to time. Has a discontinuity, and it changes at this point, which is since it's a square, we know that this midpoint here is at L over 2, which we stated there. So we need to define our boundary conditions. So we know that at 0 would be the beginning, right when that hits that, and then we know we're going to stop at the very end of this whole thing at 0.02 seconds. But what happens in between? Well, we need to know, at this point it changes, so we need to know what time that's going to happen at. If it's traveling at 10 meters per second and this is the half length, we can take our half length, square root of 2 over 20 meters, and divide it by our velocity, which is 10 meters under seconds, and you get that time to equal square root of 2 over 200 seconds. Alright, so that's our first boundary condition right there, square root of 2 over 200, and then that's when phase 2 is going to start, and we need to know when does that change from phase 2 to phase 3, what that boundary is, and that would be here. When this loop is completely submerged in the B field, the flux will no longer change. Since current is the resultant, I'll just write this down now, the current is the resultant of its voltage divided by resistance. In this case, we can calculate our voltage as the change in flux with respect to time, and we know that we calculate our change in flux with respect to time, where we have BA and then cosine theta, our angle, where one of these three things here has to change with respect to time. So this could be the B field could change, the area could change, or the angle could change. It turns out for this problem it's the area that's going to change. So to rewrite this correctly for what we're going to be calculating, it's going to be B The cosine theta, the theta is 0, so that just moves to 1, or that goes to 1, so it's going to be b times dA with respect to time. Okay, so let's look at the first part of our problem, or excuse me, phase 1. Let's see, it travels at a rate of 10 meters per second. I did this by, let me go back to a different color block here. I did this by looking at, okay, if I divide this square in half, and let's just only look at 1/2 of it, since this is 45 degrees, as much as, let's say your position changes that way, this line here is going to change that way equally. I guess another way to look at this is if you have your horizontal length and your vertical length. If your vertical length was a function of your horizontal length, and you expressed it with a function mx plus b, there's no intercept, and your slope would be 1. So it would be actually the vertical length equals the horizontal length. So knowing that, let's look at how to calculate our area from that. So let's do some good old-fashioned kinematics, and we could state that since the acceleration doesn't change, there's no acceleration, our position could be velocity times time. Now, since we're looking at our area as actually, we're looking at half the area. We're looking at half of our square here. So let's call it 1/2 of our area. 1/2 of our area equals s squared over 2, because the way you calculate area for a triangle would be base times height over 2. Okay, so that's what we have. If they're equal to each other, excuse me, if the base and the height are equal to each other, you have s squared over 2. Then let's substitute in what s is, which would just be the velocity times the time. So we can say that, let's rewrite that, we don't need a 1/2 area, substitute in, equals v squared t squared over 2. And then from, oops, I forgot the area. Alright, so, and at this point we just find the derivative of that to find our change in area. So dA 1/2 dA over dt equals, we would be doing this with respect to t, so the exponent goes down, cancel the 2, and you end up with v squared t. Alright, now this is only half the area. If we were to calculate the change of the total area, all we have to do is multiply that by 2. So our total change in area with respect to time equals 2 times the velocity squared times t. We have dA dt equals 2v squared t. That's where we left off. So let's fill in what we know. We know our velocity is 10 meters per second. That squared is going to be 100 meters squared per second squared. So we have dA dt equals 2 times 100 meters squared per second squared, that's an m, times t. And then we can multiply the 2 in. So you have dA dt equals 200 meters squared per second squared t. And then let's just plug that into our change in flux formula. So change in flux with respect to time is going to equal our B field, which was 0.8 Tesla, oops, that's a big T, Tesla times 200 meters squared per second squared times t. And then we can we stated that our current is equal to the change in flux with respect to time times 1 over R, because we take the voltage divided by resistance to get current, and that would be, since our resistance is 0.1 ohms, that ends up being 8 times 200, which then, times T over here. So that ends up being 1600 meters squared per second squared times T. And that is the way you solve the current in the first phase. Alright, so that's only valid between 0 and square root of 2 over 200 seconds. That's where it reaches the midpoint of our loop. So, the other half. Alright, let's look at phase 2. I'll start with that. Current equals 1600 meters squared per second squared. Let's see, I believe there was a B field over. Let's just get rid of it. You don't need to worry about units anymore. So 1600 times T was phase 1. Now in phase 2, the change area decreases exactly inversely of how it increased in the first one. So what you can do is you can say, okay, so for what's only valid in the second phase, let's set up our boundary condition where when it reaches the end of that phase, which is going to be here when the part is fully submerged, that would be twice this time, which is 2 over 100. So it's square root of 2 over 100. We want the change to be 0. So looking at our T, we would modify T to be square root of 2 over 100 minus T. Now if you did this for a number that's in phase 1, you'd get a much greater change and it wouldn't be valid. So make sure that you stay within the boundaries of phase 2 between square root of 2 over 200 and square root over 2 square root of 2 over 100 seconds. So let's look at what those look like on our graph real quick. Phase 1 you have here, since the change increases with time, and then where it stops would be at the end of our boundary condition, you just have a linear slope up. The change is constant. And then for phase 2, you can see it goes down, almost mirrored of what phase 1 was, until it reaches 0, because that's where our next discontinuity of our shape changes. And actually, let's talk about phase 3. For phase 3, the part is fully submerged. It's in your B field here. There's no change in area, there's no change in B field, the angle isn't changing. So if there's no change in flux, there's no voltage generated, therefore there's no current generated. So for phase 3, within our constraints, I equals 0. So looking at all three of those on a graph, you could see here it climbs up to our first boundary, it decreases with our second boundary, and then our last phase, there's just no current. Alright, so we know that this boundary condition is where this peak is. We stated that that is the square root of 2 over 200 seconds, so we can easily solve what our maximum current is by just putting that value into our phase 1 or phase 2. Either one will work. Let's do phase 1, it looks easier. 1600 times square root of 2 over 200 seconds. And that ends up equaling something like 11.31 amps. So lastly, we just need to declare at what point in the position that occurs, which is how we found our boundaries in the first place. So that was L over 2. I don't know if you remember, L was equal to square root of 2 over 10. So 1/2 L equals square root of 2 over 20. So that would be the position along, as it's traveling, that we would have our maximum current.